Welcome to our YouTube channel. Today, we're delving into a fascinating and unique subject that sheds light on one of the greatest engineering and construction mysteries in history: the building and operation of the Great Pyramid of Giza. Have you ever wondered how the ancient Egyptians managed to lift and transport those massive stones and intricately place them to construct the iconic Pyramid of Giza? In this video, we'll explore a novel and innovative theory about the pyramid building process, centered around harnessing the power of water. We'll highlight the use of advanced hydraulic and mechanical techniques to efficiently lift these colossal blocks using the force of water. Were these techniques even possible in that ancient time period? And what could be the potential purpose behind this remarkable engineering feat? Join us on this journey as we uncover the secrets of the construction and operation of the Great Pyramid in a way that hasn't been revealed before. Don't forget to subscribe and hit the notification bell to stay updated with our latest content. Let's together dive into the world of ancient engineering mysteries and achievements. In our quest to unravel the mysteries of the Great Pyramid, much attention has been devoted to understanding its dimensions and layout, which have been thoroughly explored and documented. However, a crucial aspect that has eluded a comprehensive understanding is the method by which the colossal stones were transported during its construction. To grasp the sheer scale of the pyramid, consider this visualization. If constructed using small bricks, it could provide enough stones to erect a wall 20 centimeters thick and 3 meters tall spanning the entire United States from the Pacific to the Atlantic coast. According to Herodotus, the construction of the pyramid spanned 20 years, translating to a relentless delivery of 40 tons of stones per hour, 24/7. This staggering volume prompts us to question how these massive stones were transported to the construction site. Examining ancient Egyptian transport methods, it becomes evident that the Nile River played a pivotal role as a primary transportation route for goods. It's conceivable that floating objects, including the pyramid stones, were transported along the river. Moreover, it is plausible that locks were employed to facilitate the extraction of these floating objects from the water. To begin our exploration of stone transport methods, let's consider the distance these stones traveled in water as they ascended from the river to their final destination within the pyramid. This serves as a logical starting point in unraveling the intricate processes employed by the ancient builders. By delving into the dynamics of water transport and the potential use of locks, we aim to shed light on a critical aspect of the pyramid's construction that has remained enigmatic until now: water lock technology. Throughout history, water transport has been a preferred method, especially in areas with comprehensive river and canal networks. An integral part of any canal system is the water lock, a technology designed to manage level differences and facilitate the movement of floating objects, even uphill. When navigating upstream along a river, the energy derived from the downward flow of water is typically abundant. However, in cases where it is limited, the efficiency of the water lock becomes crucial. The key to efficiency lies in the careful adjustment of the sizes of both the floating object and the lock itself. This ensures that all the water introduced into the lock contributes effectively to the lifting process. A water lock essentially functions as a counterweight system. When fully optimized, a floating package can be lifted by lowering an equivalent weight over the same distance. There are three main variants of lock systems, where lock sizes are tailored to the dimensions of the floating object, and gates move vertically. Closed lock. This is the most energy-efficient lock system, operating like a pulley where one lifted object is exchanged with another lowered object of the same weight. The lower gate of this lock must withstand high water pressures, depending on the lifting height. Open lock. This is the least efficient system, utilizing additional water equal to the volume of the upward step. Synchronized lock flight. When several open locks are connected in series, an overall gain in efficiency is achieved. This system, using additional water equal to only one of the upward steps, optimizes the process. During the peak of canal transport in Britain, sophisticated lock systems were developed to address water scarcity issues. Examples include the caisson lock and side ponds, introduced during a period when canals were being phased out and replaced by railways. These technological advancements reflect the ingenuity of adapting water lock systems to overcome challenges in transportation and water management. In addition to energy efficiency, the speed of transportation is a crucial factor. When dealing with objects one by one, the synchronized lock flight method stands out as significantly faster. Enhancing the overall speed of any lock system can be accomplished by scaling up the lock size to handle multiple objects in a single operation. The transportation of stones in water necessitates a floating support. When the water is saturated with salt, the weightless floating support must roughly match the volume of the stone. Typically, the density of the stone is 2.4 grams per cc, while the density of salt water can be around 1.2 grams per cc. Consequently, the ideal container needs to be weightless and possess a volume approximately double that of the stone. This consideration is pivotal in ensuring the efficiency and effectiveness of the transportation process. The need for a weightless, buoyant container of suitable volume underscores the intricacies involved in transporting stones in water, particularly when accounting for variations in water density due to factors like salt content. By addressing these factors, we aim to optimize both the speed and efficiency of the stone transport, providing a comprehensive understanding of the logistics involved in this ancient engineering feat. Waterlock types, optimizing efficiency in navigation. Waterlocks are crucial components in managing water levels and facilitating the movement of vessels through different elevations. Understanding the types of waterlocks is essential for efficient navigation. Here are three main types. A. Open lock. An open lock operates by using additional water equal to the volume of the upward step. In simpler terms, to lift an object, let's say a boat or a cargo, 4 units of water are required to descend, providing an efficiency rate of 25%. This means that only a quarter of the water used contributes to the lifting process. B. Synchronized lock flight. The synchronized lock flight is designed to enhance efficiency. It uses an additional water volume equal to a single upward step. In a practical scenario, this design achieves an impressive efficiency rate of 67%. Compared to the open lock, it requires less water to achieve the same lifting effect. C. Closed lock. The closed lock stands out for its superior efficiency as it utilizes no additional water. With an energy efficiency rate of 100%, this lock type ensures that every drop of water serves the purpose of lifting the vessel. It's an environmentally friendly and resource-efficient solution. Each lock type comes with its own set of advantages and efficiencies. While open locks are less efficient, synchronized lock flights offer a significant improvement, and closed locks stand out as the most environmentally conscious option. Choosing the right type depends on factors like water availability, environmental considerations, and the specific needs of the navigation system. Remember, the efficiency of these locks not only impacts the operation but also plays a role in sustainable water management. Throughout this video, the provided values are rounded and approximate, but they closely align with the actual measurements. The aim is to describe and validate the methods. Unless specified otherwise, pressure values are given as absolute values, with normal air pressure set at 1 bar. For every 10 meters of water depth, the pressure increases by 1 bar. The first machine, 20 meters to 40 meters. The examination of the dimensions and features of the Grand Gallery, GG, with waterlock methods in mind reveals a fascinating discovery. This room was purposefully designed to accommodate a synchronized lock flight. The cross-section, measuring 8 meters in height and 1 meter in width at the top and bottom, perfectly aligns with the design of the locks and their moving gates. The paired niches on the sides indicate the gate positions, serving as anchoring points for transverse beams and gate scaffold rigs. These transverse beams served various functions: dividers between the locks, lower back support for the gates, and guides for water flow beneath the lifted gates. To fully adapt the lock space to the floating package size, stone steps were placed at the lock bottom, supported by the transverse beams. This arrangement gave the canal a staircase appearance when empty with lifted gates. The 4-meter-tall vertical side walls in the canal were also constructed from removable stones. Longitudinal niches on each side wall, located 4.4 meters above the base, served as foundations for the platform where gate operators stood. This platform also acted as an upper back support for the gates, which were 4 meters tall and 1 meter wide, manually operated from above. The platform width allowed for one operator between each gate, and with every other gate being operated simultaneously, 2 operators could handle each gate. With 25 gates in total, This led to a team of 27 operators managing gates in the GG. About 30 operators were required for lifting stones 20 meters, and the layout was meticulously tuned for optimal energy efficiency and effective operation. An animation provides an overview of the machine states, illustrating the transport from the Queen's Chamber, QC, to the King's Chamber, KC. The mechanism for transferring packages from the horizontal corridor onto the locks in the GG was a complex construction. The niches served as fixing points for transversal beams, providing clues about their function. The system operated as a closed lock, with gate function facilitated by stuck packages. When the lock was drained, water pushed the packages in the 1.6-meter high corridor, inserting the next package into the lock. Upon refilling the water, the packages were pushed back, and a pawl, made of a wooden plate, prevented the return movement. This mechanism worked like a ratchet, ensuring the chain of packages moved only one way. The output gate was similarly constructed, using a stuck package as well. The operations were rhythmic and synchronized. A physics data simulation is employed to demonstrate and validate these operations, focusing on the most complex part of the transport, the transfer from the horizontal corridor to the GG locks. The simulation confirms the utilization of intricate waterlock techniques in this ancient engineering feat. The second machine, 40 meters to 60 meters. The first machine successfully lifted stones to a height of 21 meters. The subsequent machine had a more limited lifting capacity, managing 18 meters, precisely to the top of the King's Chamber, KC. During stone transportation, the 5 upper ceilings in this room were not yet installed. This machine operated as an open lock, specifically designed to handle a batch of packages. The lifting height was determined by the input gate's ability to withstand pressure when the lock was filled with water. At 18 meters in height, the pressure on the gate slightly exceeded 2 bars relative, generated by the weight of the salt water. The gate had to endure a load of more than 20 tons. Upon the delivery of a batch, the input was sealed by 2 packages, supported by 3 wooden boxes. These boxes could slide up and down in adapted niches in the side walls and were further supported by a transverse granite stone. While current documentation does not explicitly mention significant back support in the floor, a 300-year-old drawing in this figure precisely shows a recess providing this necessary support. The removal of this recess from the floor might have been intentional, possibly to prevent stumbling when visitors entered the KC, concealing a crucial clue about its function. The robust construction of the input gate was essential to withstand the pressure, and only a few operators equipped with boat hooks were needed to operate this second machine. A data animation offers an overview of the states of both machines, illustrating the operations in the pyramid. The most renowned artifact in the pyramid is arguably the granite box in the KC. Did it serve a technical function in the operations within this room? Considering its physical dimensions, it seems capable of floating, or at least being easily movable in 1-meter deep saltwater when empty, serving as a solid anchor when filled with water. Operators managed the packages as they arrived in the KC, taking advantage of a water depth of about 1 meter, making the packages easily movable but not fully floating. When a batch was received, the entrance was blocked by 2 packages to create water plugging. This setup posed some challenges. Relying on a standard package for a watertight solution was not sufficient. There was a risk of these packages moving out of the entrance tube during lifting. There was a risk of the plugging collapsing with severe consequences, potentially causing up to 1,000 cubic meters of water to flush down the Grand Gallery, GG. The solution involved using an oiled piece of leather to cover the opening, clamped in place by the granite box. This repurposed, partly broken sarcophagus not only improved watertightness but also, in case of a plug collapse, significantly reduced the water flow down the GG. Communication between operators in the Queen's Chamber, QC, and King's Chamber, KC, and the outside was essential. The pyramid builders utilized air shafts, similar to ship's tubes for communication between the bridge and the engine room. The optimal location for the water tube was in the floor. This drawing by Benoit de Maillet in 1735 provides a unique glimpse into the pyramid. What particularly catches the eye is the specific detail clearly showing a recess in the floor, seemingly designed to support the input gate of the King's Chamber in the upper part of the drawing. This element is absent in later documents, making it a crucial point for understanding the structure and construction processes inside the pyramid. The floor recess appears as an integral part of the structure, where it could serve as a necessary support for the input gate of the king's chamber. This discovery raises questions about why it is not mentioned in later documents. Perhaps it was intentionally removed to avoid confusion or interference with later explorations of the pyramid. In any case, this drawing serves as significant evidence of the design and engineering accompanying the construction of the pyramid, shedding light on details not apparent in later records. Transport container and stone size. The stones were transported using reusable standard-sized containers, which posed the challenge of ensuring a robust airtight seal. One potential solution involved filling the interior with leather balloons, with the stone placed in the lower part to allow the container to float stably. Besides its role as a transport container, it served as a closed gate when intentionally stuck. The containers had multiple functions, and their transport through corridors prioritized smooth ceilings and walls over a finished floor. All level references were related to the ceilings. Two standard container sizes were utilized, with the Grand Gallery (GG) machine capable of handling both sizes and the King's Chamber (KC) machine designed for the smaller one. The base size for both containers was determined to be 1.0 meters by 1.3 meters, with standard heights of 1.1 meters and 1.6 meters. These containers could carry loads in salt water of 2.5 tons and 1.7 tons, respectively. The stone sizes were influenced by the sizes of the containers and the internal transport machinery. The outer casing stones and backing stones had consistent heights on each course, while the inner core stone sizes were more challenging to measure. Above the 35th course, stone heights ranged from about 50 centimeters to 100 centimeters, sizes manageable by the internal machines. The stone density was assumed to be 2.4 grams per cc in this video, although actual measurements for limestones in the pyramid indicate a lower density close to 2.0 grams per cc. This adjustment affects the maximum stone volume values, considering the tare weight and volume of the container itself. Power supply. The challenge in lifting massive stones for the construction of the pyramid was addressed by focusing on lifting water instead. While it might seem preferable to manually handle 1,000 kilograms of water rather than a 1,000 kilogram stone, the sheer mass of the pyramid made it impractical to rely solely on muscle power. However, the strategic location and topography of the pyramid offered a solution to the energy supply challenge through the implementation of Heron's fountain. The topography allowed for harnessing the energy from the annual flooding, akin to the modern utilization of lunar energy. The flat area between the pyramid and the Nile, approximately 8 meters above the normal river level, would be inundated during the annual flooding, with flood heights at Thebes reaching 11.6 meters. By constructing a 2 meters tall dam on the flat plateau, a reservoir with potential energy to lift the stones was created. In contemporary times, electric charge, gas, and oil are common energy carriers transported through cables, cans, or pipes. The ancient Egyptians, however, employed compressed air delivered through tubes. To overcome the lack of high-pressure tubing, tubes were created in the limestone bedrock or enclosed under the weight of stones. A series of compressors or a single large volume compressor was positioned in the reservoir below 10 meters of water, capable of delivering an air pressure of 2 bars. This compressed air served as the energy source for all water lifting operations and, consequently, the lifting of stones. Transporting the compressed air from the reservoir to the pyramid was feasible due to the moderate pressure. Within the pyramid, where higher pressure was advantageous for larger vertical steps in water pumping, an air pressure amplifier was established. The pressure chamber, known as the subterranean chamber, SC, was situated as low in the bedrock as possible, approximately 30 meters below ground level. The SC could then deliver 4 bars air pressure, created by the weight of the 30 meters water column from the moat surrounding the pyramid. The water surface in the compressor functioned like a piston. When the chamber was full of water, it was drained, and the process restarted. The draining process initiated when a floating object pulled up the plug, resembling the operation of a classical European-type flush toilet tank. The pump. Imagine the pump as a counterpart to the compressor, utilizing the weight of water to compress air. This ingenious construction had two distinct operating modes. It could either connect to compressed air or outside air, allowing it to alternately deliver or receive water. Picture a series of these pump modules seamlessly connected to the water supply pipe, each strategically positioned at different vertical intervals to match their unique lifting capacities. Directly above each pump module, the water pipe featured check valves. The brilliance of the system lay in the synchronized interaction between these pump modules, a dance of sorts. Every other module was designated either for receiving or delivering mode, creating a harmonious rhythm. As part of the Great Pyramid project, arrays of pump modules were strategically positioned outside the pyramid, driven by a 2 bars air pressure, while their counterparts inside the pyramid operated with a 4 bars air pressure. One of the primary challenges in this intricate system was achieving precise switching between the two modes. It was crucial to ensure that both air tubes were never opened simultaneously. Ingeniously, this delicate balance was maintained by mechanically linking the two plugs, allowing for only minute movements necessary to orchestrate the seamless operation. This careful coordination ensured the efficiency and reliability of the entire water lifting system within the pyramid. The boat pit pump is a marvel in engineering, designed for optimal water lifting. Let's delve into its intricacies. Tube to outside air. This is the connection to the external environment. Compressed air supply, 1 or 3 bar relative. The source of compressed air, operating at a pressure of 1 or 3 bar relative. Supply of water from previous pump 10 or 30 m below. The influx of water from the preceding pump, located either 10 or 30 meters below. Delivery tube to the next pump 10 or 30 m above. The exit route for water, leading to the subsequent pump, positioned either 10 or 30 meters above. Fig A, receiving mode. In this mode, the pump is ready to accept water. The blue color represents water, while the yellow indicates compressed air. Note the triangle, which denotes a check valve in the delivery line, ensuring a unidirectional flow. Fig B, delivering mode. Now, the pump is in action, delivering water to the next stage. The intricacies of this process involve the interaction between water and compressed air. The design of the pump could take various forms, but a common configuration involved two air openings positioned above each other, with compressed air entering from below. The pivotal element was a disc, seamlessly transitioning between stable positions. This transition was facilitated by a float with a lever mechanism, which influenced the disc exclusively when the float occupied either the top or bottom position. The float's buoyancy came into play in the upper position, while its weight took effect in the lower position. Achieving stability relied on carefully calibrating the weight of the disc and the size of the air openings. One remarkable feature of the pump was its innate ability to automatically seal off the compressed air when not in use, for instance, when water wasn't being supplied or when the pressure dropped. Managing water intake into the air tube posed a challenge when the compressed air inlet was situated below the water level. To address this, effective water drainage from the air tubes became imperative. A straightforward approach was to consistently direct compressed air upwards, allowing water to naturally flow back down to the compressor over time. Energy requirements. Let's delve into the energy demands of this monumental pyramid construction. The estimated weight of the pyramid is a staggering 60 giganewtons. To lift the colossal stones from the base level, we would require a net energy of 3 terajoules. Over a construction period of 20 years, the average net energy needed annually was around 150 gigajoules. To put this in perspective, this amount of energy is equivalent to the potential energy stored in a reservoir that is just 1 meter deep and positioned 10 meters above the normal river level, covering an area of only 1.5 square kilometers. In practical terms, the project likely consumed more energy than these theoretical calculations suggest. However, the topography played in favor of the endeavor. The map indicates that a reservoir size exceeding 70 square kilometers was feasible between the Giza plateau and the riverbed. Examining the topographic levels, height above river level, between the river and the pyramid, we find the river at 0 meters, the riverside at 8 meters, the reservoir rectangle spanning from 3 to 7 meters, and the pyramid base at 54 meters. This topography provided an optimal setting for constructing the dam. Interestingly, the water supply to the reservoir might not have solely relied on flooding. A horizontal canal extending south along the valley side could have served as an additional water source beyond the flooding period. Covering a length of 100 kilometers, it would reach a point where the normal river level was 10 meters higher. Beyond meeting the project's water needs, this canal could have also facilitated transport and irrigation. The existence of such a canal would significantly reduce the required reservoir size, adding another layer of ingenuity to this extraordinary undertaking. In this map, it is evident that the expansive region between the pyramid and the Nile River is well suited for containing a water reservoir exceeding the stipulated volume. This location serves as a significant reference point, emphasizing the remarkable capability of leveraging the terrain to achieve the monumental engineering feat of this project. The area of the depicted rectangle is approximately 70 square kilometers. The SC compressor. Overview. The SC space is irregular, with a stipulated volume of 200 m³, including the connected horizontal corridors. The operation cycle involved 3 states: draining, priming, and delivering. Draining. The drain size and plug specifications are unknown, assuming a square cross-sectional area of 0.5 square meters. Lifting the plug under 4 bars pressure, requiring a force of 150 kilonewtons, presented a challenge. An object with this buoyancy would need a volume of 15 cubic meters, an impractical implementation. The solution involved releasing pressure with a lever mechanism close to the ceiling, operating on the air input valve. Fulcrums for this mechanism remain in the SC. With reduced pressure, a 2.5 m³ object providing 25 kilonewtons lifting force was sufficient. The drain plug, float, and rig were square but rotated 45 degrees relative to the room layout, placed inside a recess in the floor. Priming. After draining, the chamber contained air at normal atmospheric pressure, 1 bar. Priming to achieve a 4 bars delivery state could occur in various ways. Simple filling. Adding 150 m³ of water from above resulted in a potential delivery volume of 50 m³ of compressed air per cycle. Air priming. A faster and more energy-efficient method involved initial priming with air to 2 bars from the 2 bars compressor, followed by 100 m³ of water, yielding a delivery volume of 100 m³ per cycle. Using air directly from the 2 bars compressor, rather than lifting water, significantly reduced overall energy consumption. Alternative setup. Attempting alternative 2 in an automatic setup faced challenges. 2 bars wasn't sufficient to open the water input valve. An additional step was needed, opening the air delivery tube, resulting in priming to 3.5 bars. This pressure acted as the set point to open the valve. After repressurizing the delivery tubes, the system was ready to deliver 100 m³ of air at 4 bars, providing 100 megajoules of energy for lifting stones. A buffer chamber connected to the 4 bars output line supplied air for the 3.5 bars priming. The connected delivery tubes and pumps contributed to this volume. Priming with air, instead of water, ensured the complete locking of the drain plug before water was introduced. Inflow valve. It was crucial to halt the water inflow during the drainage process. A valve in the water supply line, situated at the junction between the descending and horizontal corridor, served this purpose. The challenge was to create a valve that closed when draining commenced and opened when the priming process was complete. The valve module took the form of a rectangular box, seamlessly integrated into the corridor and easily removable for maintenance or replacement. Inside the box, a hinged disc was mounted. The disc was designed akin to a section of an airplane wing, considering various physical properties that influenced its operations. Dynamic lifting force from the water flow. Force from the pressure difference across the disc. The size of the output opening in the module. The weight and position of the stone that provided the main torque to open the valve. The primary objective was for the disc, from an open position, to swing closed when the pressure drop across the module reached 2.5 bars. This pressure drop occurred at the onset of draining, with a high flow generating a lifting force on the disc. As the disc was slightly lifted, the increased counterclockwise torque from water pressure abruptly pushed it to swing into the closed position. The secondary goal was for the disc, from a closed position, to swing open when the pressure drop across the module was less than 0.5 bars. This was achieved by mounting a heavy stone on the disc, creating torque against the static torque from the 4 bars pressure. The output opening in the module served as a flow restriction. A smaller opening resulted in a higher pressure drop, even for low flows. The disk specifications were influenced by this for achieving the two goals. Calibration of the valve module took place in the tunnel named Trial Passage. A 5-meter-tall water column created a 0.5 bars pressure drop across the valve, serving as the tripping point. Calibration involved adjusting the size and position of the stones and/or the size of the output hole. This site featured a vertical tube used for observing and manipulating the valve. The overall objective was to attain a valve tolerant of significant flow without closing, a property directly impacting the CFM of the SC compressors. A model is created to illustrate the operations of this valve. The SC inflow valve serves as a critical component in the intricate system. Its operation involves two key positions: the closed and open positions. In the closed position, depicted here, the valve is strategically shut off. This closure occurs during the drainage phase, preventing water from flowing into the system. The valve's design, resembling a section of an airplane wing, enables it to efficiently resist the dynamic lifting force generated by high water flow. On the other hand, in the open position, the valve allows for the free passage of water. This phase is crucial during the priming process, ensuring the chamber is ready to receive water for the subsequent delivery cycle. The design incorporates thoughtful considerations, including the force exerted by the pressure difference across the disc and the size of the output opening in the module. This illustration provides a visual understanding of the SC inflow valve's functionality, showcasing its pivotal role in managing the flow of water within the system. The controller. The control mechanism found in the chamber may appear disorganized to modern observers, leading to the misconception that the chamber was left unfinished. However, this section is arguably the most intricate and refined aspect of the entire project. It serves as the foundation for an automated control system that allowed the compressor to operate autonomously. In a contemporary automation system, a controller typically comprises sensors, logic components, drivers, amplifiers, and actuators. The SC controller's logic, however, was ingeniously implemented using levers positioned on fulcrums. These levers were responsive to sensor forces on one side, initiating actions on the other. Actuators, in turn, influenced valves or additional levers. The positioning of the lever on the fulcrum determined both force amplification and the distance of the actuator's movement. The implementation of force amplifiers, water level sensors, and timers was relatively straightforward. However, a more intricate element was the pressure sensor. This complex component could involve a robust setup featuring a leather balloon counterbalancing a stone in a water tank, suspended at one end of a lever. As pressure increased, the balloon would contract, causing a downward force on the sensor side, which would translate into an upward force on the other side. This sensor could accurately register the chamber's pressure at any given moment, regardless of whether the chamber contained air or water. It could function either in an analog or switching mode. Is this person standing in the pressure sensor cavity? And looking into. Photo by John and Morton Edgar, 1910. The disordered section of the SC is the least publicly documented part of the pyramid. To investigate how the controller was configured, it is essential to have a detailed topographic map of the floor, and hope that the structure is mainly intact. Also, the air tubes are not found. Their sizes are, unlike the water tubes, only in the range of centimeters. The force to plug an air tube is proportional to the area of its cross-section. Every 1 bar pressure difference requires 10 N for every 1 square centimeter. Here, the delivery mode will last until the water level reaches the ceiling. Here, draining. The valve to the outside air opens. The drain plug is lifted by the float. The increased water inflow closes the valve. Here, priming with 2 bars air. Here, the 4 bars air valve opened when 2 bars were reached. Inflow of 4 bars air. Kicks the water inflow valve open. Delivery mode. Speed. The compressor played a crucial role in lifting stones above the 20 meters height, constituting 65% of the pyramid's volume. The required net energy for constructing this upper part, relative to the 20 meters level, amounted to 1.6 terajoules. This energy requirement translated to 300 megajoules per day for 15 years. Consequently, the compressor had a window of 8 hours to complete each cycle and provide this energy. These calculations assume a constant energy usage during the construction period, resulting in a higher delivery rate of mass to the lower levels than to the upper ones. However, these calculations presuppose 100% effective energy use. As observed, the water locks in the pyramid exhibit an energy efficiency in the order of 50%, doubling the compressor's required workload. This implies one cycle every 4 hours or a delivery rate of 400 liters per minute with 3 bars relative pressure, 15 cfm 44 psi. For reference, a typical modern home-use compressor can deliver half of this airflow. These specifications represent minimum requirements. It is highly probable that the SC compressor operated at a much shorter time per cycle at maximum speed. The water flow through the significant drain took only a few minutes, and the priming of air was much faster. The duration of the rest of the cycle was determined by how quickly 200 m³ of water could flow through the input valve without closing it. Consequently, adjusting this valve was a critical task to achieve a high CFM. Every compressor benefits from having a decent buffer tank storage. In this case, a large pressure tank would eliminate energy delivery problems during peak transport activities. SC compressor conclusion. The SC compressor stands out as arguably the most complex and intriguing component in the project. Thanks to the controller, it operated as a fully automatic system. The various elements in the compressor were finely adapted to each other, creating a robust chain of functions. An unanswered question remains: did its controller also manage interactions with the other pyramids? Relieving chambers. When the final stone reached the top of the pyramid, the open water lock in the KC was modified to its present state with installed sealing plates. The challenge now is to comprehend the purpose of these plates. Additionally, did these granite stones serve a function during the transport phase? A crucial point is that these stones are separated from the surrounding pyramid core, enclosed within a room with limestone roof and walls. This setup allowed for repositioning the stones. A plausible explanation is that these stones formed robust watertight walls in the tall water lock during stone transport. Unlike limestone, these granite walls could withstand the many cycles of filling and emptying of water, enduring shifting forces and scrubbing from moving packages. The lowest ceiling was constructed first, followed by the one above it. To achieve this, the upper part of the lock was wider than the lower part. The number of stones in the ceilings matches the number needed to create the extended walls. After repositioning the stones, the open space they left behind was filled. The ceiling plates contributed to reinforcing the horizontal stability of the originally large open room. Water systems. 3 independent water systems were employed in the construction of the pyramid. The first system involved water flowing from a large reservoir to the river, generating 2 bars air pressure. The second system constituted a closed circuit of water circulating from the pyramid moat to the SC, subterranean chamber, and back, producing 4 bars air pressure along its route. The third system was a closed circuit for water in the locks responsible for transporting the stones. This particular system utilized salt water to enhance buoyancy. The grotto served as a connecting point between the 2 pumping systems. During construction, it facilitated the connection of water drained from the Grand Gallery, GG, to the 4 bars pumps and water from the pyramid moat to the 4 bars compressor. Later modifications resulted in its present state. One open connection from GG to SC and another from the pyramid moat to the pumps. This configuration played a crucial role in the overall plan. Here, we have a schematic representation of the pyramid levels along with an overview of water flow and compressed air distribution. The 2 bars compressor is responsible for lifting water to supply the 4 bars compressor. The 4 bars compressor, in turn, has the capability to lift salt water, depicted in green, within the pyramid in increments of up to 24 meters. It's important to note that valves, buffer tanks, connected air shafts, and intermediate tanks are not depicted in this figure, as they play additional roles in the intricate system. Herodotus, who visited the pyramid when it was already 2,000 years old, provided an account of its construction. He mentioned a 10-year period during which subterranean chambers and a 925-meter-long, 18-meter-wide water canal with 15.4-meter-high side walls were constructed. These chambers in the bedrock likely correspond to the pump modules, boat pits, water tanks, and connecting tubes. Herodotus described the construction of the pyramid in steps, resembling battlements or, as some called it, altar-wise. After laying the stones for the base, machines made of short wooden planks were used to raise the remaining stones to their positions. The first machine lifted the stones from the ground to the top of the first step, where another machine received and conveyed it to the second step, and so on. The upper portion of the pyramid was finished first, followed by the middle and then the lower part nearest to the ground. Herodotus's machine description aligns with the concept of internal waterlock machines. The single easily movable machine lifted stones between the main 20-meter levels, including the large granite stones. These stones, too big for internal transport, were delivered at the beginning and followed the construction progression. Herodotus emphasized that the first base was finished before the machines were used, allowing for larger stones. The construction sequence he described aligns with the logical process of final trimming and polishing of the outer limestone, proceeding step by step downward. Understanding the described transport methods reveals a grasp of the technological capabilities involved in the construction of the pyramid. This understanding allows for a more detailed discussion of various elements related to the pyramid project. Big stone transport. The transportation of large granite stones from Aswan to Giza involved floating them on the Nile. Contrary to a common misconception, it's likely that the stones were transported submerged in water, taking advantage of their buoyancy. A method similar to that used during the transportation of Cleopatra's Needle in 1877 involved encasing the stones in a floating device. This could be a vessel with ropes holding the stones, or even using the hull upside down with the stone underneath. The use of the solar boat is also considered for this purpose. Side ponds in the KC. Examining the energy costs during the lifting process in the King's Chamber, KC, it becomes apparent that without intermediate water storage, the cost would be prohibitively high, with an efficiency of only 5%. Introducing side ponds halfway up would significantly improve efficiency, and theoretically, an infinite number of intermediate storage tanks could achieve 100% efficiency. The placement of intermediate tanks at various intervals affects the overall energy efficiency of the system, with tanks every 1 meter resulting in 50% efficiency and tanks every 2 meters resulting in 33%. These discussions shed light on the sophisticated engineering considerations and innovative solutions employed in the construction of the pyramid. The third machine, 60 meters to 80 meters, 100 meters. Upon examining the first two machines, it becomes evident that the transport was not continuous. When the KC lock was lifted, the GG locks had to go into standby, and the transport was carried out in batches. The QC, with its delivery tube and the KC, could handle a batch of 40 pieces. To maintain the pace, this third machine needed to receive this batch without delay, likely using the same setup as the first machine. It's plausible that the receiving room and tube were designed similarly to the QC with its delivery tube. The receiving room and the KC would have a shared gabled roof, with the two galleries side shifted and positioned on opposite sides of the pyramid's centerline. This arrangement ensured that the two long and tall rooms were not directly above each other. The second, synchronized lock flight, had a smaller size since it didn't handle both stone sizes, and above this level, only 8% of the pyramid volume remained. There's also a possibility that this lock system transported stones all the way to the 100 meters level, completing 98% of the pyramid volume. Pumps and tanks. Certain pump modules took the shape of a bottle to avoid weak corners, with a curved enclosure and a long, narrow form enabling a lintel ceiling and an internal lever to operate the valves. The maximum lifting capacity depended on the input air pressure. If water was needed in a level lower than the pump's nominal maximum, it was more efficient to supply it into buffer tanks in levels where the water was used. The internal water flow description suggests that the pyramid has numerous cavities for water buffering, likely of the same height as the actual course. The cavities were filled with materials such as glass marbles to achieve a compact and stable building structure. This type of particle filler, found inside the pyramid on multiple occasions, can contain water, or air, in 25% of the total cavity volume. Purpose. Even if one of the old classical riddles about the pyramid, the transport method, is solved, many others remain. There are numerous theories about its purpose. A skyline monument, a tomb, a water pump, a power station, a water park fountain, or maybe more than only one of these. After the building was finished, several major modifications were made, probably to achieve some function. The 15 meters tall open KC got several compact ceilings. The entrance to the QC was closed. The entrance to the GG from below was tightly plugged with massive stone blocks. The main entrance was also closed. All small openings to outside, like air shafts, were closed by mortar. The grotto got a masonry creating a direct tunnel from the GG to the SC. These modifications are clues to the purpose of the pyramid. They created a tall, watertight, and airtight internal enclosure. This has been regarded as means to keep grave robbers out. But, if we turn it around, it could also keep stuff contained, solidly enclosed under heavy stones. The rearrangement of the grotto created a 70 meters tall water column all the way from the KC to the SC. If water was delivered to the KC level, the pyramid compressor was upgraded from 4 to 8 bars. If also pressurized air was delivered, the output pressure would increase accordingly. The fact that the Great Pyramid delivered energy, compressed air, to build the other two pyramids is obvious. When they were finished, did the three pyramids operate coordinated? Did this cooperation enable them to deliver compressed air with even higher pressure? Obvious questions are: what was this high-pressure air or water used for? Had the Sphinx in its pool a super impressive fountain on its back, or a singing siren? Did the pyramids supply power to an industrial stone carving machine? A water jet machine with a stationary jet and moving floating workpieces? Located nearby in Zawiat El Arian? Was the pressure high enough to cut and polish granite precisely and speedy with a narrow water jet nozzle? This description of the transport system is supported and verified by the fact that river location, pyramid location, topography, room layouts, room sizes, internal details, and stone sizes all are contained, and the speed requirement is met. Also, it matches completely the description given by Herodotus. It is fascinating to imagine the building activities accompanied by sounds from pneumatic machines. The compressors and pumps sounded like steam engines in very slow speed. Some components to complete the system, like tubes for compressed air, are not yet found. The shafts we see today were found by chance. They were originally closed and sealed. The transport system used a wide range of technical methods in a standardized and modular way, also using methods we today consider modern. The classical physics laws of Heron of Alexandria, Archimedes, Boyle, Marriott, and Bernoulli are demonstrated in practical use. The modifications to the building, after completed construction, indicate that the pyramids were used as either air compressor or high-pressure water pump, delivering a pressure as high as the pyramid could contain. The layout of the plant was fully adapted to the topography of its location. The building got an internal design that was perfectly trimmed and tuned for its functions, not only for the construction period, but also for its production period. Every little bit of the project was planned. Some critical elements were even prefabricated, as it was not possible to lift them after the building started. The workforce was trained personnel with a wide range of professions. Project planning and implementation were done by people with skill and endurance. Ankhaf and Hemiunu are considered prominent project leaders in the building of the Giza pyramids. Portraits from ancient Egypt were mostly stylized. These 4,500-year-old portraits are exceptions. And there you have it, standing on the brink of a universe filled with mysteries and incredible engineering feats. The Great Pyramid of Giza remains a symbol of human capability to face challenges and showcase creativity in constructing such colossal structures. This new theory about the pyramid building process offers us a different and innovative perspective on how this remarkable achievement was realized. If you've enjoyed this video and want to explore more intriguing content about historical mysteries and engineering, feel free to subscribe to the channel and leave your comments and thoughts in the comment section below. Thank you for tuning in and joining us on this exciting journey. Let's continue together to unravel the wonders of the past and understand how ancient civilizations shaped the contours of our modern world. Until next time, don't forget to subscribe for more updates.